All right, guys, welcome back. Fasten your seatbelts. We are about to study the wonderful world of matrices. Chapter 16 is all about matrices, and in general, the whole time that we deal with Chapter 16, we're basically trying to find ways to solve systems of equations. And those systems can have two variables, they can have three variables, or they can have more than that. So our goal is to find efficient ways to solve these. So to start off with, we're going to look at some old methods like elimination of variables to solve. Then we'll move ourselves into using determinants and something called Cramer's rule. And then finally, we'll use inverses of matrices to do that. And along the way, we'll define what matrices are and we'll find some of their operations to help us get to those various stages. Okay, so let's remind ourselves about how we solve systems of equations with two variables in the past. And remember that these are just lines. So when I'm trying to solve a system of equations, I have three different scenarios that can happen. The first one is they can be parallel lines, which means they have no solutions. Remember, solutions are just points of intersection, points that are the same on both things. So if they're parallel, there's no solution. If they actually intersect, then two lines will intersect to form a point or one solution. And if they're concurrent or the same line, then they have infinite solutions. Basically, any point on the one line will be a point on the other. So those are our three things that can happen. So let's look at how we can actually solve this. Now, this slide looks a little overwhelming, so just hang in there and let's start at the top. So the top is just a system of equations, and I've color-coded it to help you a little. The red coefficients, or the red values are coefficients on x, the blue values are coefficients on y, and then the c values in green are constants. So we're assuming that they're not zero. If they were zero for those coefficients, then they would basically make our equations just 0 equals 0. So we're assuming that they have value. Okay, so to solve this, most of the time you guys would start with one of the equations, I'll pick the first one, and you would solve for one of the variables. In this case, I'm going to solve for y. So I solved for this y by bringing over the x term and then dividing by the coefficient on y. Then I'm going to use substitution to plug that back into the second guy. So I'm using my y value and plugging it in here, and you can see me plugging it in there. And then I'm going to multiply both sides by this denominator so I can get rid of it. So I'm multiplying every single term by b1. So that adds a b1 to this guy, the b1 cancels here, and I have a b1 here. Then I'm basically just working my way through solving for x. So like I multiplied this out, I took the term that didn't have an x to the other side, I factored an x out, and I solved for x. So I'll give you a second to kind of look through that. You can hit pause if you need to. Okay, so what we have found out is that one way to get x is this relationship. So we've got a product here minus a product on top over a product on the bottom. Now, of course, this would only be true for a solution if the bottom wasn't 0, because obviously we can't divide by 0. We can use the same reasoning. I'm not going to do it, but we could use the same reason to find a solution for the y value. And the y value solution looks very similar. Notice they have the same denominators, but different tops. Okay, so there's a way that we can solve and get those solutions. And we do this when we have real numbers. It's just I'm showing you here with the variable coefficients. Again, we've discussed further in the past how to tell if the system has no solutions, which is when you're, if you use linear combination, you get your variables to drop out, but you get something that says like maybe 5 equals 0, which means that can never be true. So there would be no solutions. And then if you have the same idea, but you end up with a 0 equals 0, that's when they're the same line, which means that you have infinite solutions. So you can revisit that. I don't think that will be hard for you to tell. Okay, so you could memorize those formulas that we have on the previous page, but that really isn't an efficient use of your time. You guys know how to solve systems as they are, so you don't need that formula to help you. But the formulas will play a part in determinants that we use later in this chapter, so it's just a little sneak peek. Okay, we can apply these same ideas to three space. And so if you want to look at the solving the equations that I created on the previous slide in three space, you can do that on page 392. But I'm just showing you the scenario. So we have no solutions, we have one solution, and we have infinitely many, just like we did for 2D. So in 3D, no solutions could look like this first scenario where your three planes never intersect together, because remember, they would have to intersect together to be a point of intersection or a solution. So this is a no solution scenario. One solution would be when you have your three planes all meet at a point. So like you could think of it as this. If I look at the pi 1 and the pi 2 plane, they meet at this line, but that line only intersects this plane pi 3 in one point. So this one's intersection is a point. And then last but not least, you've got this last one down here where the three planes are kind of like spines of a book, if you want to think of a book flayed open. And so those three planes meet to actually form a line. So that's the infinitely many solutions scenario. And we've talked about this in the past with using planes and vectors and whatnot, but just showing you how we would, how that would look. Okay, so as promised, after we talked about elimination and solving it that way, the old way is we can use determinants. So let's talk a little bit about what those look like. So if I wanted to find a matrix, so a matrix is an m by n matrix specifically is an array, a rectangular array of elements with m rows and n columns. I'm going to get rid of that. A rectangular array of elements with m rows and n columns. And so it looks kind of like this. I wanted to draw it and it was a little bit easier to draw. So this would be, I'm going to let the elements each be like a subscript something. So A1, 1, this would be A1, 2. It's not 11 and 12, it's 1, 2. And then this would keep going. And then this next one would be A2, 1, A2, 2. And then I could keep going down this way as many as I wanted. So if this had m rows, my last one would be a sub m1, a sub m2, and then this would go all the way until a sub mn. Now, how does that work? These are just locator values, guys. So like if I ask, these are just the elements. So an element is denoted by its position. So if I said element a sub 4, 5, that means I'm looking for the element that is in row 4, column 5. So I would go down to row 4, column 5. So when I say A sub 2, 2, I don't mean 22, I mean row 2, column 2. So you want to think of matrices again as having rows all the way down to row M, and then columns, column 1, column 2, column N. Okay, so it's just a rectangular array. The order of a matrix is defined as m by n. Two matrices are considered equal or equivalent if and only if they have the same order. So they have to have, sometimes we call this the same size, and each corresponding element is equal. So like if I have two matrices, make these little 2 by 2s, 2 rows, 2 columns. These are equivalent matrices because they have the same size, 2 by 2s, and each corresponding element is equal to each other. Okay, so that would be what we would consider equal matrices. Okay, so now we'll focus on the determinant of a matrix. A determinant of a matrix, it takes a square matrix, so that means your rows and columns have to be equal, okay, and maps it to a real number. So it gives us a real number from a particular square matrix. And we've done this before. So if I've given a matrix A, so here's my matrix A, if I want to denote the determinant of A, which sometimes can be denoted like this, I just put what looks like an absolute value around my matrix. And that means that you're taking the determinant of A, and from the last unit, you guys might remember that the determinant of A is the product of this diagonal minus the product of that diagonal. And again, remember, this is a real number value. Okay, so that's your determinant. So now, something called Cramer's rule allows us a more efficient way to solve the systems that I was talking about earlier, using 2 or 3 or more variables. So, okay, let's go back to this one that we were remembering from earlier. So here was our initial situation. Remember, this goes back to the pages that we had done before. We had said that x was equal to this and y was equal to this, okay? So another way of thinking about this, I don't know if you guys are noticing, but these little values are determinants. Like this value right here is the determinant if I used A1, B1, A2, B2 as my matrices. See that? Because that would be A1, B2 minus A2, B1. So that bottom, actually for both of them, is the determinant of this guy, the coefficients on x's and y's. So there we've got those. This one, I'm going to probably prefer to use this. It's a little bit more straightforward. So our bottoms are the determinant of the coefficients, and then let's check out the tops. Now, the original Cramer's rule uses this. If I want to switch the orders of the columns, then I have to make it negative, otherwise the order is different. Basically, I'm just doing like this minus this, and if I switch them, it switches the order. So it's like taking 3 minus 5 and switching it for 5 minus 3. But that one comes out to a -2, so then I would have to make this answer the negative version if I want these to match. That's kind of what I'm doing here. So anyways, okay, so the reason I like this reordered with the negative is because then you can just use the matrix right here. right, which are already close to each other. So then I'm doing the determinant here. This times this minus this times that. And then for the y value, you're using the coefficients on x and c1. So you're in the c values, the constant. So you're going to use those two together, and you're going to use that 2 by 2 determinant. So there's another way to get our solution using Cramer's rule. Now, let's try one. Once again, you do not have to use this, but it's another way. So let's try one. Okay, so if I want to solve for my x value, then, and actually I can do both x and y right now. So if I want x and y, I'm going to do the determinant of my coefficient. So I'm going to create the matrix 2, 4, negative 3, 7 for the bottom for both of them. And on top, for x, remember it's negative, and I'm going to use the y values and the constants. So 4, 18, 7, and negative 2. And for the y values, I'll use the x coefficients and the constants. So 2, 18, negative 3, negative 2. Okay, so let's try it. Let's do it. The determinant of my first guy is going to be, I'll have a negative out front. I've got negative 8 minus, 126. And then on the bottom, I'm going to have 2 times 7, 14, minus negative 12. Okay, so on top, I have negative 134, so that's positive 134 over, what do we got down there, 26, which I can definitely reduce to, what do we got, 77? No, that's not right, 67. There we go. Okay, so there's my solution for x. Now let's do y. Well, y is going to have the same thing on the bottom, we already know, so that's easy. So 14 minus negative 12, so we've got 26 on the bottom. On top, we've got negative 4 minus negative 54, which gives us 50 over 26, which gives us 25 over 13. And then we could, of course, check our solutions. I think one of the easiest ways to check your solutions would be to just plug them back in. So by that I mean, like, I'm going to plug in 67 over 13 for x, so 2 times 67 over 13 plus 4 times 25 over 13. And let's hope we get 18. And we sure do. And I won't waste your time, but we could also try it for the second one and make sure we get out a negative 2. And then that would be an easy way to check. You could also graph these in your calculator by solving them for y and doing the intersect feature and seeing if you get out the same values. So that's another option. So do you have to use this to solve every time? Certainly you do not. It is a way to solve. You could also use elimination. Like I can multiply the top guy by 3 and the bottom guy by negative 2. So it's just another way of using matrices to solve. Okay. Obviously something in 3-dimension might be a little bit more difficult. Okay, check out this relationship. So this relationship is a 2 by 2 determinant, and it's saying that that value is 0. So let's see if we can solve this. And you can pause it and try it yourself if you want, and then pick back up. So we're going to multiply x by x minus 2 times 3, 6, should come out to 0 is what that's telling us. So I end up with something like this. I can factor that into x minus 3x plus 2. So my two solutions would be 3 and negative 2, and of course I could plug them in and make sure that that was true. So another kind of way to use the determinant. All right, so you might be asking yourself, can we solve a system with 3 variables the same way? Of course, the answer is yes, you absolutely 100% can. You can do third order determinants, 3 by 3s. You would need them, of course, to solve this. I will just remind you how to find 3 by 3 determinants again. So doing this, I did a shortcut and then a little bit longer version. So let's say finding the determinant of the matrix 2, 1, 5, 3, negative 1, 2, 4, 3, 4. Okay, so one way to do a 3 by 3 determinant is to expand your matrix. So basically continue on so that you can create the proper diagonals. So you're going to rewrite column 1 and you can then rewrite column 2. So this is just me doing the drawing so that I don't have to like fold the diagonals on themselves. And so we're going to treat this as the same as the 2 by 2, which is I'm going to look at the product from the top left. So I'm going to take that product, which is -8. I'm going to add it with the next right to bottom diagonal, which is 8, plus that last one, which is 5 times 9, so 45. So that is all my top left to bottom right diagonal. And then I'm going to subtract my other diagonals, which are my bottom to top. So I've got -20 plus 12 plus 12. So up here I have 45 minus down here I have 4. So 41 is my determinant. Okay, so we can also solve this. You might remember me working with the smaller minor matrices within a 3 by 3. And so let me explain. So again, you can work with this minor of an element of a determinant by creating 2 by 2 matrices, eliminating rows and columns. So let's remind you how that looks. So here's the one that we had previously, except I think that middle guy is a -1. Okay, so we have to understand two things. Number one, the minor, and the minor is what you get when if you pick an element, like 2, for example, I would eliminate the row that 2 is in and the column that 2 is in, and then this 2 by 2 determinant that's left over, or the 2 by 2 matrix that's left over is called the minor. Okay, we have something called the cofactor of an element. The cofactor of an element is, of a determinant, is the minor multiplied by 1 or -1, okay? And so we decide if it's 1 or -1 by taking the sum of the row and column of that element and deciding if it's even or odd. If it's even, it's 1. If it's odd, it's -1. You'll see this in a moment. And then finally, generally, the determinant is just the sum of what you get. So when I add together the products of the element that we choose, so, and it can be of any row or column. So if I want to use this first row, I have to use all the elements. So I'm going to use 2 and do this process, 1 and do this process, 5 and do this process, and then do the sum. I could pick any row though, guys. I could start with 3 and use all the elements in that row, or I could pick 5 and do all the elements in this column, and should get the same determinant no matter which one I use. I prefer to use all the elements of the top row. When we did vector cross multiplication or cross product, excuse me, we used the first row as ijk to create that relationship. So you're probably most comfortable. Okay, so let's try this. We know from the previous page that the determinant should be 41. But let's see if we get that using this minor version. So if so, my determinant should be found by taking the product of the element. So I'm going to start with my element in my first row that I'm going to use the entire row, 2. Then times, let's see, and their corresponding cofactors. So now we need to find the cofactor for element 2. So first thing is I need the minor for 2. So the minor for 2 would mean I get rid of the row of 2 and the column of 2, which leaves me with this 2 by 2. So that is going to be the minor, and I'm going to take it's the determinant of that. So -1, 2, 3, 4 times 1 or -1, depending on if that particular element has a row and column sum that's odd or even. So what do they mean by that? Well, if you're using element 2, where is element 2? It's row 1, column 1. So this is like A sub 1, 1. So if I add together the subscript 1, 1, 1 plus 1, I get 2, which is an even number. So that means I would just multiply this guy by a 1. Okay, that's my first part. My second guy, pick the next element. So I'm going to pick 1. So I'm going to take the element 1 times, let's do this part first. So if I'm trying to figure out if I should have a 1 or a -1 here, this position is row 1, column 2. So sub 1, 2, which would add up to 3, which is odd. So you're going to multiply by a -1. This is where the negative in front of the j came from when I was doing the cross product using vectors. And then times that 2 by 2 minor. So the minor for this middle element, get rid of this, would be 3, 2, 4, 4. Okay, and then last but not least, I have my last element of my row, 5 times, this is the row 1, column 3, so that would be sub 1, 3, which adds up to 4, which is even, so that last guy would be by a 1, and then that minor, get rid of the row, get rid of the column, would be 3, -1, 4, 3. Okay, let's give it a go. So we have 2 times, the determinant of this guy would be -4 minus 6. So -4 minus 6 gives me -10 plus, oops, nope, -1. So minus 1 times, this would be 12 minus 8, so 4, plus 5 times, the determinant of this would be 9 minus negative 4. 9 minus negative 4 is plus 4, which is 13. So then we have negative 20 minus 4 plus 65, which does in fact give us 41. Yay, we knew it would. So this sounds more complicated than it actually is. Like most people, when they're doing this, they just do 2 times, like they look at it and go 2 times this determinant, boom. 1 times that determinant, but that middle one is a negative, like they get used to that rule. So most people find doing the determinant of a 3 by 3 easiest to do by hand using this method, okay? If you want to read about some cool corollaries, they're on page 401 in your book, and they can just show you how you can work with 3 by 3 determinants. They're pretty cool. And there's also a proof for Cramer's rule, the one that we used a couple of pages ago to solve for variables for a 3 by 3 matrix on page 402. So if you want to look through those, you can. So again, now we've come up with a way to solve 2 by 2 and 3 by 3 systems of equations using matrices, determinants specifically. Okay. Okay, so let's get into some more general algebra with matrices, which by the way is denoted as linear algebra, which is a course we offer here. Ms. Doshek teaches it, and so if you're interested in going further with matrices, you could take that later on in your math studies. Let's first look at addition. So we're going to do some operations with these matrices. So two matrices can be added or technically subtracted. We'll talk about what that means if and only if they have equivalent dimensions. So for example, you can add a 3 by 4 with another 3 by 4, but you can't add something that has two different dimensions. Okay, so let's see this in action. So let's say that we start a school store and you're selling t-shirts and shorts and hats. So I made a matrix of that and you're selling them at lunch and after school. So my matrix here is just for one day. So it shows the sale. I changed this. It shows the sale over, it shows the sale at lunch and after school for both items. Okay. So this is just one day's worth of sale. Okay. So if I wanted to add the next day's sales, but still be able to compare lunch versus after school and the different items, I would need to add a matrix of what size? So this matrix, I guess we should start with this. This guy is a rows by columns, a 2 by 3. So if I wanted to add the next day's sales, but again, be able to still see lunch and after school and still see each item, I would have to add another 2 by 3, right? That's the only way that we could add them. Otherwise, I wouldn't be able to see everything. Now, of course, I could add total t-shirts, total shorts, total hats, but that's not really what I was asking in this one. Do you think it would matter what the rows and columns referred to in the one that you were going to add, or does it just have to still be a 2 by 3? Well, in this scenario, if I wanted to keep my matrix representing the same items, then yeah, of course, my 2 by 3 would still have to have lunch here, after school here, and then t-shirts, shorts, and hats in that order. If it wasn't, then they wouldn't correspond. So doing operations with matrices is all about having things that correspond to each other correctly. Okay, so matrix addition is pretty easy. I don't foresee you guys having any issues with that. So for example, if I had 12, 2, 7, 6, 0, 9, and I added the second day's matrices, which are maybe 1, 6, 4, and 0, 0, 7. Hats were going like crazy the next day. My result would just be to add corresponding elements. So I'd have sold 13 total t-shirts for lunch, for both lunch times. I would have sold 8 shorts at lunch and a total of 11 shorts at lunch over both days. Then 6 after school, 0, man, shorts were not popular after school, and 16 hats after school over both days. Okay. You can do subtraction the same, but with subtraction, we don't really think of it as subtraction. We think of it more as adding the negative version of this matrix. So if I wanted to subtract and find the difference in sales, that's a way of doing that, then I would just make this -1, -6, -4, and -7, and then I can add them still, but get that result. Okay. So what if I estimated that I would sell roughly this same amount over the next 2 weeks of school? How could I quickly find the totals for each? Well, 2 weeks would be 10 days of school, so we could take 10 times each of these items, right? So this is called scalar multiplication, and so we're literally taking the number 10 times our matrix, and this is how we write that. So this is called a scalar, just like we did for vectors. And all that means is that each item is going to get multiplied by 10. So this would be your rough estimate for how much you think you would sell over the next 2 weeks of school. Okay, so there's addition, there's subtraction, there's also scalar multiplication. So just some general properties of addition, assuming that A, B, and C are all matrices and they all have the same order. So that's important. So it won't matter whether you add forwards or backwards. So addition for matrices is commutative. This is a big one. There's a special matrix 0, the 0 matrix, such that if I add the 0 matrix to A, in either direction, you just get A. This is something you guys should have used in the past in math. When you add something and you get out the original thing you had, that's just called an additive identity. So an additive identity is just something that you can add that gives you the original value back out. So it doesn't change it. Okay, for each matrix A, there exists a matrix negative A, which is basically just your matrix times -1, such that if I were to add them together, I get 0, or the 0 matrix. Remember, the 0 matrix would just be a matrix full of zeros. Okay, the matrix negative A, of course, then is called the additive inverse, because the additive inverse completely undoes or gives you zeros, or does the inverse operation of having that matrix in the first place. So that's an additive inverse. And then here's this last property is just associative, which means you can add these two first and then those two, and then the C last or vice versa. And so the grouping won't matter. You'll still get the same thing. So property is important. Okay, for scalar multiplication, again, A and B are matrices. They have the same order, and X and Y are just real numbers. So again, if you have numbers in front, it doesn't matter if you multiply the number the matrix first, or you multiply the two real numbers first and then multiply them by the matrix. Same thing, you could add the real numbers first and then, or you could add the real numbers first and then multiply, or you could distribute to the matrix to each of them. Same thing here, you could distribute the scalar to each of them. And then multiplying any matrix by 1 just gives you A, obviously, and any matrix by 0 gives you the 0 matrix, which would be an empty matrix. Okay, basic operations. Okay, so matrices part 2. If you need to take a break, you can take a break and come back. We're getting into a heavy part, which is matrix multiplication. And so if you need to take a break and come back and watch this, please do, and try some of those exercises from the first part, and then you can come back to matrix multiplication. Okay, for those of you that are ready for matrix multiplication, if you haven't done this, this is a little different. Matrix multiplication in brief is basically a row by column multiplication. That's the general version. So how do we do that? When we're multiplying two matrices, so they can just be next to each other, that means to multiply them. So I'm going to use the rows from the first and the columns from the second. So I'm going to start off with row 1, and I'm going to multiply row 1 by column 1. And so the way that I do this is I start with the first element here. So I'm going to multiply row 1, the elements in row 1 by the elements in column 2. And then I'm going to take row 1 times column 2, and so on and so forth. Okay, so I end up with, in my first position, I'm going to take 1 times 6, and then add to that 2 times 3. So it's almost like dot product, like I'm taking the dot product of that vector and that vector. In fact, it kind of is for some things that you might do later, but okay. So I'm basically taking the dot product of this vector and that vector. So 1 times 6 plus 2 times 3. Okay, that is all my first position. This is using row 1 with column 1. So it shouldn't shock you that using row 1 with column 1 produces row 1, column 1. All right, what if we wanted to produce row 1, column 2? We would use row 1 with column 2. Same thing, dot product. So 1 times 8 plus 2 times 1. And that produces row 1, column 2. Okay, then we're out of columns. So we're going to go on to row 2. So now we're going to do row 2 with column 1, which would produce the element for row 2, column 1. Dot product, here we go. Negative 4 times 6, negative 24 plus 5 times 3, 15. So again, I'm doing the dot product of this vector and that vector is another way of thinking about this. So the last one is this row with the last column. So row 2, column 2 should produce position or element row 2, column 2. So here I go. dot product, negative 4 times 8, negative 32, and then plus 5 times 1, 5. So my final answer for my multiplication then is 6 plus 6, 12. 8 plus 2, 10. Negative 24 plus 15, negative 9. And negative 32 plus 5, negative 27. So that's what I get when I multiply those two matrices together. Okay, not too shabby. If you want to try the next one on your own, I'll help you get started. You can hit pause. So in my next one, let's check it out. We always use the rows of the first, so I'm going to have 2 rows to use and only 1 column. So before you hit pause, you should know how many rows and how many columns your output should have. It should still have 2 rows and only now 1 column. So we'll see how that works out. So if you want to pause and try it on your own, you can. All right, let's work through the answer. So to get row 1, column 1, which it's my only column, so I would take the dot product of those two vectors. So 3 times 1 is 3, plus negative 1 times 5, plus 5 times 6 is 30. Okay, that's all row 1, column 1. Now notice there are no more columns, so there's no more columns. Go on to row 2. Row 2, column 1, dot product of those two vectors is going to be 4 minus 40 plus 0. And then there are no more columns, so we're done. So my final result is only a 2 by 1. I have 3 minus 5, which is negative 2, plus 30 is 28, and 4 minus 40 plus 0 is negative 36. Crazy, right? Because you have two matrices that are coming down to something small. Now, I don't know if you guys noticed this, but one way that you can determine what's going to happen here is you can write down the original dimensions. Like this is a 2 by 2 times a 2 by 2. And my result was a 2 by 2. Okay. That may not be as obvious. Let's look at this one. This is a 2 by 3, and this is a 3 by 1, rows by columns. Now, the result for this one was a 2 by 2, but the result for this one was a 2 by 1. Interesting. Wonder if we can use those to help us decide what our result is going to look like. Well, let's look at this last one and see if this helps us. Okay, if I was going to do this last one, I would use my rows and my columns, right, guys? So let's get started. All right, my first one would be row 1, column 1. So if I go to do this, what's the problem with trying to do dot product here? Yeah, this has 3 elements and that only has 2. Uh-oh, we cannot do matrix multiplication. It's undefined, basically, because I can't do it. There is no third. There has to be a third element to match up with the 5. So let's see what happened here. This one was a 2 by 3 times another 2 by 3. So let's see what the problem was. Well, the number of values here, which were technically columns, like this was 1, 2, 3 columns, didn't match up with how many rows I had here, which, guys, can be described as inner dimensions. So if these didn't have inner dimensions that match, meaning the columns here didn't match the rows here, and if that doesn't happen, you can't multiply. So as long as these inner dimensions match, you can multiply. So that's why this one can't. Now the other cool part is, check this out. The resultant rows by columns, rows of the first, columns of the second, is the dimensions, or are the dimensions of your result. So the outer dimensions of the multiplication was 2 and 2, so we resulted in a 2 by 2. That's because you're using rows and columns. So the number of rows here were 2, by columns 1, so my result is a 2 by 1. Again, I couldn't do this one, so I couldn't have a result. You will get much more practice with matrix multiplication by hand later. Okay, so once again, since matrix multiplication is only defined if the columns of the first and the rows in the second, or the inner dimensions, match, let's take a look at what that looks like. Like if I have a 2 by 3 and a 3 by 1. So again, this will work because my columns from my first and my rows from the second, or the inner dimensions, match. This works, but look what would happen, guys, if I try to switch the order. Uh-oh, that does not work, because now my inner dimensions don't match. So I can't switch orders and just expect everything to still work correctly, which means that it's not commutative, right? So matrix multiplication is not commutative. You can't switch it switch the order. Like I can't do A times B and B times A and get the same thing. That's not true. But there are some things that do hold. So associativity does hold, so you can group them differently and still get the same answer. For the second line here, if this holds, so that means if you can add these two together and then you can multiply that result by A, meaning they have the inner dimensions that match, then you could also have distributed it and it would have worked. Same thing just with A on the right-hand end. Okay? Okay, so let's try some identity matrices. So there is a matrix I, capital I, that's called the multiplicative identity for matrix multiplication. Now remember, the identity is usually when you do the operation with it and you get the same thing you started with. That's an identity, right? It's identical to the beginning. So could you think of what that matrix might look like? And what I mean by that is, here's matrix, here's the identity, here's what we're looking for. If I take that matrix times A, I still get A back out when I multiply. Or if I multiplied A by I should still get A. So it shouldn't matter whether you multiply by the identity out front or afterwards, you should still get back out A. Can you think of a matrix? And I'll make up one here real quick. So I'll make matrix A 3, 4, negative 5, 8. So you're looking for a matrix that you could multiply and you'd still get out 3, 4, negative 5, 8. If you want to pause now and try a few of these on your own, you can. So a lot of you probably started by guessing 1, 1, 1, 1, right? That might make sense. But the problem is you end up with, you have to multiply, remember, row 1 with column 1 to get here, and that's 3 plus 4. So the problem is you do want the 3, but you don't want the 4. So you might have said to yourself, well, let's make that 0. So then that gives me 3 plus 0, which is just a 3. Okay, that works for that one. What about for row 2, column 2? Row 2, column 2 should give us 4. But right now I have 3 plus 4. I don't want the 3, so maybe I could make that a 0. So that would be 0 plus 4. Yep. Now let's see if it works for the second row. So if I do it for the second row, that would mean I'm using row 2, column 1. Row 2, column 1 would give me negative 5 plus 0. Yep, that's negative 5. And if I do it here, so that does work out. So this is the identity matrix. It's a 2 by 2 identity. A 3 by 3 identity would look like 1s on the diagonal as well. So basically your identity matrix has 1s on that top left to bottom right diagonal, and that will give you the original matrix back out. So that's really important, and we refer to that as the I matrix. And so I've got those here for you to take a quick look at. So again, this is called the identity matrix. And so it could keep growing. So from what we did earlier, you might be asking yourself, if there's a multiplicative identity for matrix multiplication, is there a multiplicative inverse? Now remember, inverses, if I go back to something really easy, let's say I had 5x equals 10. If you wanted to get rid of multiplication, you would do the inverse operation, which would be division. Or you could multiply by 1/5, right? So 1/5 is the multiplicative inverse of 5. So that's a way for us to kind of, solve equations, right? So you're looking for this, basically you're trying to get this down to a 1. Now we don't really write 1 when we solve, we just put x, but we're getting rid of this so that the coefficient is 1. Now why do we care about 1? Well, 1 times x doesn't change x, we just get x. So we're looking for a value that will just give us out something that when multiplied by this doesn't change it, so that we can finish solving for it. So is there an inverse, a multiplicative inverse for matrices? Yes, there is. Good question. So inverse matrices, because that's basically what we need, are denoted a lot like inverse trig functions. So remember how we had sine and then sine inverse, which meant to undo sine? Same thing for matrices. This is nothing. For matrices, we had A and A inverse. So this is the inverse matrix for A. So what that means is if I were to multiply A with its inverse, it should give me the identity, which we talked about on the previous page. Or if I multiply the inverse by A, I get the identity. So we need to figure out how the heck do we get the inverse for a matrix. So we're going to use our old friend's system of equations to find the inverse. So let's do it. Okay. So let's say this is our original matrix and we want to find A inverse, right? Okay, we'll let A be this, and we're going to try to figure out what this matrix is. Now, these, I just filled them with some variables for the moment, and we'll figure out what these actually are in a little bit. But what we do know is that if I multiply these two things together, I should get the identity matrix, which means if I take that matrix times that one, I should get 1, 0, 0, 1. Okay, so let's actually multiply these out and see what that looks like. And I'll have to use matrix multiplication to do that, obviously. So, okay, so let's see. So if I'm going to start with row 1, column 1. So if I take this and dot product with that, I get AW plus BY for my first position, which means if I look over here to the other side of the equation, I should get a 1. Hey, that's just an equation. So I'm not actually going to write this as a matrix equal to this. I'm just going to write it as the equation. This times this should give me 1. All right, let's do the row and the second column. So I get dot product of those two is AX plus BZ. And that should give me row 1, column 2, which is 0. Keep doing multiplication. Row 2, column 1. So dot product of this guy with that guy is CW plus DY. Gives me the row 2, column 1 position, which is 0. And last but not least, row 2, column 2 should give me that element, which is 1, which is the dot product of those and those. So CX plus DZ. Okay, so now I have a system here using W's and Y's, which is what I'm trying to solve for, and a system here using X's and Z's. So let's use Cramer's rule. So let's bring back Cramer's rule. Okay, let's see if you remember it from earlier. If not, that's okay. I'll help you. So Cramer's rule says this. If you have two variables, which remember, technically we will know A, B, C, and D, so they're not really variables. So my variables here are the W's and the Y's. So if I want to use Cramer's rule to solve for W, you're solving for the first variable. Because we wanted this to work in order, if you remember, we had to make the X, or in this case the W term, negative on top, but we did negative the determinant of this matrix, meaning the coefficients here and that, so B1, B1, D0. So I use that guy. And then the bottom was the determinant of this 2 by 2. Again, we're talking coefficients, so A, B, C, D. Okay, so that would be how I could get W. I could get Y in the same way, except when I go to solve for Y, I use this 2 by 2, and I don't have to flip it because it's already in order. So it's A1, C0 over the same thing, the determinant of this 2 by 2. Okay, and then I'm going to do it here for those two variables. So if I want to solve for X, remember when I'm solving for the X of the first variable listed, I had to switch it, which means it has to become a negative version of the determinant of this matrix. So B0, D1 over the determinant of this 2 by 2, which, hey, is still A, B, C, D. For the second variable, Z, I don't have to flip it this time. It's of this 2 by 2, so A0, C1 over that same determinant of the coefficients. All right, so let's bring it all together. So what does that mean? All right, that means that the W position, okay, let's do the actual determinant. I get 0 minus D, but minus D times a negative would be positive D. So in my matrix, I get D over this. But guys, remember, ABCD is just the original matrix. So basically, that part on the bottom is just the determinant of the original. So I'm going to say determinant of A. That's my first position. My next variable, though, is X, the one that goes here. So I'm going to go over here. This determinant is B minus D, which is B, but I have to make it negative. So negative B over, once again, the determinant of the original, A. All right, my next variable that was here, my next element was Y. So the determinant is 0 minus C, so negative C over determinant A. My last position was Z, which is A minus C, so A over determinant of A. Whew, now, determinant of A is just a number, like it could be 5, it could be 7. So I can bring that out front. So I'm going to bring out the determinant of A, but remember it's technically a division, so I'm going to do 1 over the determinant of A, and I get this. So let's compare this. I've got a better version here. Let's compare the inverse. That's what we were solving for. Remember, guys, so we just found the values of the inverse. The inverse of a 2 by 2 matrix is 1 over the determinant of the matrix, of the original matrix out front. And then look what happened. If this is my original, A and D just switch places. And then B and C stay where they are, but they both ended up being negative. This is called an adjoint matrix. You don't need to worry about that now, but that does have a name. So this is how we get the inverse of A. And a 3 by 3 version of this is proved on page 416, but we'll just use our calculator to get it. So I'd like to try one. Let me see if I gave us one to try next or not. Yeah, I did. Well, let's do one on our own. So I'm going to insert a little page, and then we'll come back to this one in just a second. So let's try a determinant just to make sure that you guys are comfortable with, let's try finding an inverse just to make sure you guys are comfortable with it. So let's start with the matrix. I'm going to call this one B. And let's start with the matrix 4, 5, -3, 2. Okay. So to get B inverse, the first thing I would need would be 1 over the determinant of B, and then I would multiply that by that adjoint matrix, which is switch A and D. So this is going to be 2 now and 4. And these guys stay where they are, but they become the opposite sign, right? You get multiplied by a negative. Now we have to figure out the determinant of B. So we've got 8 minus -15. So not the most beautiful inverse, because this ends up being 1 over 23. And then this is a scalar, so I could distribute it. So I'd get 2 over 23, -5 over 23, and 3 over 23, and 4 over 23. And remember, when I multiply this with B, I should get the identity matrix. That's the whole point. So I should get 1, 0, 0, 1. Now, I think this is a good point to show you guys that you can do a lot of this on your calculator. And I want to show you how to do that. Oh, one quick thing before we get to our calculator. Can you guys think of a time or a part of this inverse relationship where we wouldn't be able to find an inverse, or the inverse would be undefined? I'll give you a hint. It's right out here. There's a division. If this value is what, this whole thing would fail. 0. That's right. So if your determinant of your original matrix is 0, it's over. So your determinant can't come out to a 0, otherwise you can't find an inverse. So just note to self. Okay, so let's look a little bit about how we can do some of this stuff on our calculator. Good times. Okay, I'm going to do a few things and then I'll go on to the last little part. Okay. All right, so let's go first to our matrices place in our calculator. So we find matrices, see here's matrix, by going second x inverse. And then we've got some columns that are names, math, and edit. Names are what you use to actually do the operations. Math are the operations, and edit is where we can create the matrices. So I'm going to go over to edit, and I'm going to edit matrix A. And so first you have to tell the dimension. So I'm going to start off with a 2 by 2. And if you hit enter, it'll just go to the next one. And then you just type in and hit enter, and it works itself across. So like if I want to do the matrix 1, 5, if I do a negative, I do have to use the negative symbol, so be careful of that. -3 and 2. Okay, so there's my A matrix. So, unless, you know what, you can hit quit. That's the easiest way to get out. I'm gonna go back in and I'm gonna edit another one. So I'm gonna get a matrix B ready. And I'm going to do 2 by 3. And so I'm just going to throw some numbers in here. 3, 4, 1, 0. I'll do a -2 and a 4. Okay, so now I have a couple matrices in there. So I'm going to quit. All right, so let's say you just want to do scalar multiplication, which most of you can do by hand. So like you wanted to multiply matrix A by 3. You can just say 3 and then go back into matrix. This is where you're going to use name. So then you're going to use the name to call it up. And so then you can just take your matrix times 3. Again, I think you can do that by hand. You can also do division, but you have to do it as a fraction. So like if I wanted to take a fourth of my matrix, I could do 1/4 times A. There's no such thing as division with matrices, so you have to do it as multiplication. So there we go. Now, hey, maybe you're saying to yourself, I'd really love to have these as fractions instead of decimals. Guess what? Math to frac works on matrices, so you can also change your matrices into fractions. What? Okay. Let's say if you wanted to add matrices, obviously we could say, A plus B. I can't add A and B. Why not? If you want to add matrices, they have to have the exact set of corresponding elements, and this one doesn't. It's a 2 by 3, and this one's a 2 by 2. But what if I wanted to multiply a 2 by 2 with a 2 by 3 in that order? Could I? Well, let's see. Inner dimensions, 2 by 2 do match. So I can multiply A times B. So I would do A, and then you can either put the multiplication symbol, or you can just write it next to each other, because that means multiplication as well. So however you guys want to do that. So here I am. So that means A times B. So here I go. If you couldn't do it, it'll give you an error. Like if the inner dimensions didn't match, it'll tell you. So there's my matrix multiplication. Whoa! That means finding matrix multiplication, you can check your work. I mean, if I want to see the work and you have to prove it on a test or something, you're going to want to show me. Especially if I start introducing variables, you wouldn't be able to do it on a calculator, but you can check your work, of course, on the calculator. How about inverses? You bet. If I wanted to find, remember, you can only find the inverse of a square matrix. It has to be square, meaning like 2 by 2, 3 by 3 to find its inverse. So I can find it of A, I can't find it of B. So let's do it. All right, so now as you might have guessed, we're going to get weird fractions because we have 1 over the determinant out front. But if we do math to frac, we can change that thing back into the 17ths. And it will reduce. So sometimes you might see some of these denominators look different because like if the denominator was like 18, for example, instead of 17, maybe some of them would have reduced, but some of them wouldn't. And this one I can tell the determinant was probably just 17 because of the way it looks. But anyway, so you can find inverses and stuff here. So now this is cool. So that means if that's the inverse of A, then if I took that answer times A, what should we get if we take an inverse with itself, multiplied by itself? The identity, and we do. So it's a really cool way for you to check your work. Okay, so matrices are here under matrix math. Let's just show you what's their determinant. So determinant is there. This is something called transpose. A lot of these you're not going to do now, but we talked about, I think, row echelon, reduced row echelon back when we were solving a little bit. But anyway, so those are all here, but you'll use most of those if you do a linear algebra class. But that's how you use your calculator with matrices. And we're going to do a lot more. But there you go. Okay. So, we're almost there, guys. Let's bring it all together. Finally. How can we apply matrices to solve systems of equation? Okay. It involves both matrix multiplication and inverses. Okay. So let's consider this system of equations, which we started way at the beginning. And I know this is an easy one. We're really going to use what I'm about to show you more for 3-variable equations, which take longer by hand, but obviously a 2 by 2 you could just use elimination. So look at these matrices. Here's a 2 by 2 matrix, 2, 3, 4, 5. The X matrix I'm calling XY, and the B matrix I'm calling 5, 7. Notice there's a relationship here. Let's take the equation matrix A times X equals B. What would that look like? So that means I'm using these guys. So that would be 2, 3, 4, 5 times matrix X, which is a column matrix, XY. And then we have the column matrix equals B, so 5, 7. If I did the multiplication, let's see. Row 1, column 1 gives me dot product of 2, 3xy would be 2x plus 3y. Should equal row 1, column 1, which is the element 5, and row 2, column 1, which is 7, would be this row with this column, 4x plus 5y. Hey, what does that look like? It looks like those guys. That's exactly right. That's what I wanted you to see. So the matrices at right are actually, this first matrix is all of the coefficients from your system, right? So in order, 2, 3, 4, 5. That's A. The variable matrix XY are the 2 variables in order, but as a column matrix. And the constant values of your system, 5 and 7, that are not affected by the variable, are a column matrix in order, 5, 7. And so this matrix relationship was determined from those systems. Okay. So that means that if I wanted to solve for x and y, which is the x matrix, right, capital X matrix, then I would have to solve that equation with matrices. Well, how do I solve this? Well, if you want to undo a times x, you have to multiply by a inverse. And notice there's no way for me to sneak it in between here. I would have to put it on the left. So if I put it on the left over here, it also has to be on the left there, because remember, multiplication isn't commutative. So like if I can't put it, after the b, it has to be in front. If it's in front over here, it has to be in front over there. So A inverse times A gives you the identity, and the whole point of the identity matrix is that the identity times X just gives you X. So there you've done it, you've solved for it. So that means if I wanted to solve for the X matrix, I just need to take A inverse times B, and that will give me XY equals those two values. So let's try it. Let's do it. That means I need the inverse of A. Remember, A originally from the top, let's get it real quick, was 2, 3, 4, 5. Okay, so we've got 2, 3, 4, 5. And our X matrix is our matrix of variables in order, X, Y. And our B matrix was 5, 7. Okay, so I need A inverse times B. So A inverse, well, the inverse of A, remember, we're going to do the determinant, 1 over the determinant. So the determinant is 10 minus 12 times that adjoint matrix, which is switch A and D, 5, 2, and switch the signs on those guys. This is really negative 1/2 out front. So I have negative 1/2. Here's A inverse. And then remember, to solve, I have to do A inverse times B. B was 5, 7, so I can just attach it to the end. Now, scalar multiplication means I can do the negative 1/2 last. So I can just do the multiplication here and then multiply everybody by negative 1/2. So let's do it. So matrix multiplication, here we go. Row, column. Since there's only one column, we're only going to have to do each row once. So we've got dot product of this with that. So we've got 25 minus 21 for our first position. And then for the second row, we've got the dot product here, which is negative 20 plus 14. So I've got negative 1/2 out front, and I've got I've got 4 and negative 6, but I have to multiply them both by negative 1/2. So that gives me negative 2 and 3. Remember, this is the X matrix, and the X matrix was corresponding to XY. So that means your solution is negative 2, 3. Now again, that might seem like overkill, but when it's a 3 by 3 scenario, it's not as crazy. So let's try one. Let's try a real world scenario. So I said, okay, let's say you're purchasing bulk candy from a store. You're getting caramels and gummy bears, and you're going to buy 1.5 pounds of caramels and 2 pounds of gummy bears, and it's going to cost you $8.50. And your friend buys 3 pounds of caramels and 0.5 or half a pound of gummy bears, and it costs them $10. What's the price of each candy per pound? Okay, so we know how many pounds we're buying and how much it cost us, but we didn't know how much each one, the price of each one. That's what we're trying to figure out. So first we're going to set up a system of relationships or equations, and we're going to let X be the cost of caramels per pound and Y be the cost of gummy bears per pound. So, okay, let's do U first. So you bought 1.5 pounds, and we don't know the price of the caramel, so we'll say times X, plus you bought 2 pounds of gummy bears at their price, Y, and that should add up to $8.50, okay? Our second relationship is your friend bought 3 pounds of caramels, the price was X, and 0.5 pounds of gummy bears times its price, and that came out to 10. So you want to solve for the price. So here we go. We're going to set up our matrix equation. Our matrix equation would be the coefficients on X and Y as a matrix times your variables in their order is equal to our constants as a matrix. So again, good news, guys. If this is AX equals B, the way that you solve for X is to multiply both sides by the inverse. That gives you the identity. So once again, we're just doing A inverse B. This really doesn't change that much. It's almost always A inverse B. Okay, so we need to find A inverse. Now, let's cheat and use our calculator, because I want you guys to practice using your calculators too. Okay, so that means the first thing I have to do is actually put in matrix A. So I'm going to go back to Edit, matrix A. It's still 2 by 2, so that's good news. I think it was 1.5 and 2 and 3 and 0.5. Check. Yep, Okay. And then I need matrix B, so I'm going to quit this and go back in and change matrix B. But remember, matrix B was just a 2 by 1, so I need to change it to a 2 by 1, and you'll be able to tell if you did it right in a second, but okay, that was 8.5 or 850 and 10. Okay. And I have not solved this one yet, so it could be some crazy prices. Let's see. So remember, our final answer is going to be, I actually don't need to do them separately. I can just literally find A inverse times B. So that's what I'm going to do with my calculator. So here I go. So I'm going to do matrix A inverse, which is this little -1 here, this exponent, times matrix B. I'm going to call up matrix B, and let's do it. Woo! I can't believe that came out perfect. Okay, I totally made these numbers up, guys. All right, so it comes out to 3, 2. So that means it's x, y equals 3, 2. Now you would need to tell your reader what that means. That means that the price of caramels, $3 per pound, and y, which was the price of gummy bears, is $2 per pound. I still can't believe that came out. So nice. Made it up. Okay. All right. Um, Now, the other thing, just to show you, I'm not going to do a scenario on this one, but I do want to show you how you can use this with 3 by 3s because we use these with planes a lot, like intersecting points of planes. So like if you had planes, 2x plus 3y plus z equals 10, there's one plane, x minus y plus z equals 4, and maybe, 5x minus 2y minus c equals -8, right? You can also find the solution or the intersection of these three planes. And there might not be an intersection. I mean, it's not necessarily, they don't have to intersect, but I can do the same thing. So I'm going to create a coefficient matrix, which is A. The coefficients are 2, 3, 1, 1, -1, 1, and 5, -2, -1, times your variables, x, y, z. And that results in my constants. Again, here's the cool thing. Since this is A times x equals B, and we want x, we have to take the inverse on both sides. So my answer is going to be whatever the inverse of A is times B. So once again, let's go back to that handy dandy calculator, except I'm going to scoot it over so I can see my work. Okay, so I'm going to put in matrix A. This time it is a 3 by 3. And let's see, 2, 3, 1. So I'm just typing over 1, -1. Make sure you put, this is important. If you put it and even one little number wrong, it's going to change everything. So you just have to be really careful. Okay, and then I'm going to quit. I'm going to go back in and edit matrix B because matrix B is now a 3 by 1. Remember it was 10, 4, -8. So 10, 4, -8. Now if this comes out nice, I'll be shocked because I totally just made this up. Here's the cool part. If you already have A inverse B somewhere on your screen, you can hit it and it will do the new A inverse B. Otherwise, you have to type it again. Okay, good. Finally, some nasty answers. Now, once again, if I want to get the fractional version so I can be exact, I can hit math to frac. And here we are with our beautiful answers. 2/27 for x, 40/27 for y, and 146/27. So if these were three planes, guys, this would be the point where the three planes intersected, which is pretty cool. Way easier than it used to be. Okay. All right. The only time it doesn't end up really being A inverse B is like, can you imagine if you had matrix A times X plus C equals D? And these are all matrices. If you wanted to solve this for matrix X, the first thing you would have to do is move this guy over, so you would have to subtract it. And so you would have something that looks like this. Now remember, technically subtracting a matrix is the same as adding the matrix but times a negative, right? So that's really what I'm doing. And then I'd get rid of the A by doing A inverse on both sides. But of course, it would be A inverse of all of that. So you'd have to do that. But totally doable. So like most of the time it's A inverse B, but every once in a while you do get something where you have to do, something a little bit crazy. All right. Those are the basics. I'm sure that we will talk a lot in class, in our class meetings about this. And I'm excited. Matrices really aren't that hard. I just wanted to make sure I give you a really thorough explanation of matrices. Okay, I'll see you soon.